let's look at some examples in expected value. And what I'm going to be walking through here is the Blackboard activity, Marvelous Expected Value. And here's a picture of the front of that activity. So let's look at how you'd calculate these different questions, or how you'd answer these different questions. The first two questions have to do with a fair game. So let me explain fair game a little bit better. Fair game is a game where the expected value comes out to 0. In other words, both the player and the owner of the game come out even. No one's coming out ahead. So the fair price is going to be the price that you'd get, or let me go back and say a fair game is a game where the fair price is going to be equal to the expected value plus the cost to play. So if you are given a cost to play and you have the expected value, you could calculate what they should have charged to make it a fair game. This first question is really just assessing whether you understand this first bullet point, that a fair game is a game where expected value is 0. So if the expected value is 0, was he charged a fair price? Yes. If the expected value came out to 0, then that $50 was set correctly. When you have the expected value and a cost to play, you can calculate the fair price by adding the expected value to the cost to play. So for number 2, the expected value of 2 added to the cost that Black Widow was charged tells us that what they should have charged if they wanted a fair game was $7. But instead, this game, because there's a positive expected value, what that says is that Black Widow is coming out ahead. And so you can see that they're undercharging for this game. Number 3, but the first example where we're working out an expected value, we're looking at a case where you're rolling a 6-sided die. So the probability of each outcome, a 1, 2, 3, 4, 5, or 6, is 1 in 6. So there's a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling a 2, and so on. And for this example, the way that it's just defined is our gain or loss is going to be whatever shows on the die. When you say find the expected value for the outcome of rolling a fair die, then the gain or loss is just the value on the die. So if we wanted to calculate the expected value, what we would do is take each of the outcomes, and we'd multiply the probability of that outcome times the outcome itself. So for a 1, all the way up through rolling a 6. The probability of rolling a 1 is 1/6, so we have 1/6 times 1 added to 1/6 times 2 added to 1/6 times 3, and so on up through 1/6 times 6. So you could see when you multiply those that we'd end up with the 1, 2, 3, 4, 5, and 6 in the numerator and a 6 in the denominator. So when I add these, I would end up with a 21 over 6, which can reduce to 7 over 2. Or if we were writing this as a decimal, it'd be 3 5/10. 3 1/2 or 3 5/10 or 7/2 would all be correct answers, just depending on what format the directions specified. Let's look at examples number 4. We've got the same six-sided die, but now we've got a game where it doesn't say anything about playing or paying to play. So the actual how much you win or lose is the actual gain or loss. So when you roll an even number, like the 2, 4, and 6, you win a flat rate of $8. If you roll an odd number, like the 1, 3, 5, you're going to pay or owe twice the value of the roll. So you'll either owe $2, 2 times 1, or $3, 2 times 3, or $10, 2 times 5. When we write these out, we've got to consider each of the outcomes, rolling a 1, 2, 3, up to rolling a 6, and we're going to multiply the probability times the gain or loss. So that would look like this when we put the probabilities in, and then when we add in the amount, it's going to look like this, where we've got negative 2 times 1, 6, plus 8 times 1, 6, plus negative 6 times 1, 6, plus 8 times 1, 6, plus negative 10 times 1, 6, plus 8 times 1, 6. And we could multiply each of those, and notice that we end up with negative 2 plus 8 minus 6 plus 8 minus 10 plus 8. I'm going to simplify this calculation by grouping the negatives together. So altogether there's negative 18, and then noticing that there's 3 8s, because 3 times 8 is 24. So our total is going to come to 6 out of 6, which reduces to 1. When you get to the part of this question that asks whether or not Star-Lord should play, or do you think he would play, you need to understand what expected value of 1 means. So should he expect he should expect to win $1 over the long haul? On average, he's winning $1 each time he plays. So that's in his favor, but is $1 worth his time? His chance of winning is 50-50, and every time he wins, he's winning $8, which is more than he loses for a 1 or a 3. So really, if he can avoid rolling a 5, he does pretty well. If he feels like he's a lucky guy and he can avoid that 5 or use his powers to not ever let the die fall on a 5, then maybe he should play. But if he doesn't think it's worth his time, or he just doesn't like taking a risk, then maybe you'd say no. So there's multiple ways to answer that. Let's look at number 5, the raffle tickets. So these raffle tickets cost $1, and there's one prize, and only one person's going to win. So it's only $1, but out of the 1,000 people who play, there's only one winner, and that winner is going to get $500. So we could describe the two outcomes as either winning or losing. When you win, notice that the gain is actually $499. Where did that come from? Well, you win $500, but remember you paid $1 to play. So your net is $499, or what you actually gained. Not how much you won, but how much you gained was $499. And then when you paid $1 and you didn't win anything, you've actually lost $1, or your loss is $1. The probability of winning is 1 in 1,000. The probability of losing is much higher, 999 out of 1,000. So we could put the probabilities and the gain or loss in this formula, and we'd get 499 times 1/1000th plus -1 times 999 1,000ths. And when you add that up, you get 499 plus -999, and that comes to 500 over 1,000. So it looks like there's a loss of 500 over 1,000, and you should be able to reduce that to lowest terms and round to the nearest cent. So what does this mean? If I put this 500 over 1,000, I'm going to get a loss of 0.5. So if I wanted to translate that to money, it looks like on average you're losing 50 cents. So the tenth of a cent would just be negative 50 cents. Let's look at another raffle ticket where there's 3 winners. One winner will get $1,000, another winner will get $50, and a third winner will also get $50. So there's a total of 3 outcomes: winning 1,000, winning 50, or losing. So when you win 1,000, that's a chance of 1 in 1,000. Winning 50 is the probability of 2 in 1,000. And there's 1,000 minus 3 winners leaves us 997 losers. So 1,000 minus the 3 winners gives us 997 ways to lose out of the 1,000. So looking at the gain or the loss, when you win $1,000, but you paid $2 to play, your gain is 998. When you win 50 and you paid $2 to play, your gain is 48. And then if you lose, you have paid $2, so you've lost $2. We could write these values into the formula, and it would look like this: 998 times 1 1,000th plus 48 times 2 1,000ths plus negative 2 times 997 1,000ths, and we're going to get a negative 900 over 1,000. Notice how many cents that is. If I just divide by 10, I've got negative 90 100ths of a dollar. So that's going to be a loss of 90 cents. A loss of 90 cents. When the expected value comes up negative, that means that over the long haul, you'd be losing. Well, I hope that this short video has helped you with this activity. If you do have further questions, I'm happy to help you. You could visit me in the office, virtual office hours, or send me an email and we could set up an appointment. Or if it's a question I can respond to over email, I'd be happy to take a question through email also.